back. This is the second part of the same video on circularly polarized transmit array or reflect arrays. These arrays, just a reminder that these arrays are not composed of uniform unit cells. The unit cells are basically different. In part one, we covered that they can be different in size, like this one. The unit cells can be different in size, or they can be different. The size is the same, but the rotation angle of the cell is not is changing. You can see it here, like some of these ones. You can see that some of these squares, when I say rotation, what it means. Some of them are, the rectangular part is horizontal and then it slightly changes. I lost my mouse. Where is my mouse? Technical issues. Are you, where is it? Okay, I don't know what's going on with my mouse. Up here. So you can see here, like this one, for example, is on this side, this is on this side, this is on this side. Okay. Yeah, it's Teams. I'm recording this with Teams, so it's a little bit like tricky. Okay, so we covered the first case where we had squared patches basically stacked, and we called it phase delay because it was basically manipulating the X direction and the Y direction incident rays exactly the same way. Okay. Now we are covering another type. In this type, let's go back. We said we have two coordinate systems. We have one that is defined per unit cell, and it keeps changing if the unit cells patches change direction. And then the other one is for the whole array, X, Y. Okay. Now let's go back to the second case. Let's say in this case, this is another type. In this case, our one unit cell is designed in a way that the transmission coefficient along X and along Y have equal magnitude or amplitude, but they are different with 180-degree difference. Okay. When that happens in transmission coefficient, naturally you would have the same in reflection coefficient as well. But also you have the cross ones 0. So let's say you found a unit cell that complies with this, or you designed one that complies with this. X and Y equal amplitude, but 180-degree phase difference, and cross poles are 0. Now, if you put this a special case, just like we did for PD, in equations 2 to 9, which we had here, the general CP reflection and transmission coefficients in terms of linearly ones, what do you get? You get this one. These are the results of equations 2 to 9 in the special case of 19 to 21. Okay, what happens? Then as soon as you have this one, the co-polarized transmission and reflection coefficients become 0. For example, TRR, TLL becomes 0 because they have about, these two have are exactly negative of each other. The same thing on reflection coefficient, RR, oh, sorry. Now, reflection coefficient of RL, and then this one RR becomes 0, okay? I feel like there's something going on here. And then, but the transmission coefficient of cross polarization in CP, RL, becomes the amplitude of T multiplied by, what is the phase? 2 psi. What was psi? The rotation angle of the unit cell compared to the reflection, to the coordinate system of the array. For example, I'm going to draw this for you. Okay, let's say we have an array here. I hope you can see it. Let me choose another color. Okay, I have one unit cell. No. Is this a pen? Okay, never mind. I have a unit cell that is looking like this, for example. And then I have another unit cell that is compared like this. Okay, so this one, it has an angle of 0 compared to the x prime and y prime have an angle of 0. These are the unit cells coordinate system compared to x and y, which are the coordinate system of the whole array. And then here, though, the x prime and then the y prime have about 45-degree difference. Okay, so it says if x prime and y prime are along x and y, so psi is 0, then you have no phase applied to the wave in the RHCP or LHCP, basically, no phase. But as soon as the unit cells are rotated whatever degree, let's say 45 degrees, then the wave that is exciting this on the other side is going to switch its polarization and then experience twice the rotation angle of the unit cell in the phase difference, in the phase shift, basically. So this unit cell of 45-degree rotated, it would transmit the signal to the other side, switch its polarization, and then also add 90-degree phase difference. But that's what we need. We need about 0 to 360-degree phase shift, let's say, across the array, right? So all we need to do, design this unit cell and rotate it from 0 to 180 degree. Then what we would have is the wave the CP wave that is getting excited, it would switch its polarization and experience whatever phase that we apply to it. So now I'll explain it here on this phase delay one. This is, I lost my mouse again. Okay, here, this is the one. We have a phase rotation transmit array, let's call it. We are exciting it with the same RHCP feed that we excited the other plane. And then it has naturally an LHCP one. Okay, so what happens? What happens is that the RHCP wave that is getting excited, it's going to get, if we design this correctly, if it's going to get converted to LHCP and get converged to the wave. If this psi is designed based on the phase distribution that we would need. So the wave goes to LHCP, the direction, to the beam direction that we wanted. And RHCP, actually, we know that transmission of RHCP to RHCP is about 0. But because of the oblique and incidence and everything else, it would get a little bit out, but it gets diverged. Not converged, diverged, because we never designed this like that. You would also have another component. Let's go back to here. That has, you would have a RHCP in the back lobe that also gets directed to a beam, but it's less than basically the other one. The other one, both RHCP and LHCP would get converged to the same direction. Here you would only have RHCP. Here you have LHCP. So we say that phase rotations transmit arrays have a filtering effect that they would only converge one of the components of a CP wave, not the cross-pole one. So naturally, their axial ratio is better because in PD, whatever happened to RHCP would happen to LHCP as well. The cross pole would exactly follow the main beam. But in this one, the phase rotation one, that doesn't happen, right? So they have a filtering effect, but nothing comes for free, and I'll explain it later. Now let's go through an example of a phase rotation unit cell. This is the phase rotation unit cell I designed, okay? In this one, if you simulate the X direction and Y direction coefficients, you would see that they're exactly equal at this band, and then they have about 180-degree difference. Okay, it only has 3 layers, not 5 layers like the other one. It's very compact, but the unit cell is larger. And then when you convert you get the CP transmission and reflection coefficients based on equations 2 to 9, then it will look like this. So you can see the transmission coefficients, that is the main one is the cross pole one, R to L. Then, so easily we don't have the problem of like, compared to PD, we can, as I said, we can get from 0 to 360-degree phase shift by rotating 0 to 180-degree. You're like, why don't you just rotate it 360 degrees? Because then it becomes, after 180, it's just the same thing. And that's because we wanted the cross poles to be 0. That was another design requirement that we defined. Remember, we said the cross poles must be 0, and then we would have a 180-degree difference between them. So that's why we have a range of 0 to 180 degrees, and then the resultant phase shift would be from 0 to 360 degrees. So that's why. Now, you can, design it exactly the same way and then construct this array. And then now the drawback. Remember I said the phase delay one would treat the linearly polarized ones the same. So you can, a phase delay array, or TA or RA, even if you excite it with a linearly polarized wave, it would still converge for you. You would still see a beam, right? But it would be a beam linearly polarized wave. But a phase rotation one would only work for a CP wave, and it would only work when you design it for the CP, RHCP or LHCP. You can't have them both. You can't switch the feed. So if you know your feed is RHCP and might change to LHCP, then phase rotation is not good for you, right? Because once you design it for an RHCP, it's designed for RHCP. And that's what this is the drawback of this design. Yes, when you look at the simulation results here for the phase delay one, wherever the main beam is, the cross pole is in the same direction. You can see it in the dash red top figure. And then, but for the phase rotation one, as we said, you would always have some main beam close to the broadside, but not in the beam direction. So in the beam direction, the cross pole is very low. But again, you can't switch the feed. So for example, this has happened before, that an array was designed for RHCP, deployed, and then up there in the space, they had the other feed and nothing worked, right? So you have to be careful. Once printed, it's printed. You can't change it. Oh, I found my mouse. Okay. So then we did the prototype. We fed them with linearly polarized horns, and then I post-processed the results. And you can see here that in the prototype, we got even better results here. You can see about 20 dB of axial ratio or cross polarization for the PD wave, PR wave array. the phase rotation one, while for the PD wave, you can see the cross pole is going exactly the same direction, so you don't have a good axial ratio. Here you can see like the axial ratio for the phase rotation one is very low across all frequencies, but for the PD one, it has just like this one. It's following the feed. The feed is the dot black one, and then for the PD one, it's the dashed blue one, the measured, and then for the PR one is the red one. So you see, even if you have a cheap circularly polarized horn or feed, the PR, the phase rotation array, can help you to just have a great circularly polarized wave on the other side. Okay. When I say on the other side, it might mean the same side for reflection coefficient too. But with the PD, you have to have a perfect feed to get a perfect wave on the other side, because if your axial ratio is bad, the PD doesn't do anything to it. The PD has no filtering effect. So that's why. So now you're like, okay, you said all of this, but I wanted to simulate something like this. Now, as you can guess, there is no way you can design these arrays by hand. Okay. I hope I can find time to record another video on how you can use, but I'll give you the hint. You can use the Visual Basic script in ANSYS HFSS to construct this. So it would get a unit cell from you, and then automatically you can basically say, okay, choose the best unit cell that is closest to this or rotate it this much based on the phase, and then construct this, put this here, put this there, right? Because for example, for the PR one, it's easy. You just need to know a rotation and where the unit cell goes, which are two simple, basically CAD operations, right? Moving and then also rotating. For the PD one, it's even easier, but like you have to have a file or a lookup table to know which unit cell to pick based on the phase you want, and then just move it. So this is a different one. But once you construct that, then it's easy to set up the simulation as well. But there is no way, especially if the array is large, then there is no way. I hope you enjoyed this video. I hope I will find a way, time to record a third part that would be showing you at least some of the steps for simulating these structures. Subscribe to the channel, share, and do whatever you can to help this channel. Okay, bye guys.